So the next type of bond I want to talk about are polar bonds. So remember we said that polar bonds form because the electronegativity values of the two atoms are slightly different. So one atom has a slightly higher electronegativity than the other. And when these atoms come together, what's going to happen is they're going to share their electrons, but they're going to share them unequally. And this creates a polar bond. One part of the molecule is going to have a slight negative charge, one part is going to have a slight positive charge, and that's going to create a dipole within our molecule. And so let's see how that works with an actual example. And so for this, what we're going to do is we're going to take water as an example, because it's water. We've talked a lot about water, and we've talked a lot about how water is a polar molecule. And so in water, we have a bond between hydrogen and oxygen. Okay. Oxygen. Okay, so our first step is going to be to figure out the electronegativities for each of these atoms. So hydrogen has an electronegativity value of 2.1, and oxygen has an electronegativity value of 3.5. And so I want to find the electronegativity difference for this bond. And when I'm talking about a bond, I'm talking about the bond that's between a pair of atoms. So even though water has 2 hydrogens and 1 oxygen, when I figure out the electronegativity difference, I'm figuring it out for one of the bonds. And so for one of the bonds between one oxygen and 1 hydrogen. And so I'm looking at the electronegativity difference, and my electronegativity difference is always going to be a positive number. So I always want to start with the bigger number first, and I want to subtract the smaller number. So 3.5 minus 2.1 equals 1.4. Okay, 1.4 is definitely greater than 0.4. So I know it's not going to be a covalent bond. It's less than 1.7, and so this is right in the range for a polar covalent bond. So the covalent part of polar covalent means that they're going to be sharing electrons, but the polar part means that they're not going to be sharing equally. Okay, so let's actually draw this out and see what this bond is going to look like. And so what I'm going to do is I'm going to start with my oxygen molecule in the middle, my oxygen atom in the middle. And so oxygen, again, has 8 protons in the nucleus, and it also has 8 neutrons. Okay, so my neutral oxygen atom is going to have 8 electrons. It's got 8 positive charges, and so it's also going to have 8 negative charges. So let's put its 8 electrons in the shells. And so my first shell can only hold 2 electrons. So I have my 2 electrons there. And so my remaining 6 electrons have to go in the next shell. So I have 1, 2, 3, 4, 5, and 6. Okay? So oxygen is really not a happy atom yet. It wants to have 8 electrons in this valence shell, and that's why it's going to bond with hydrogen to form a molecule, because it wants to fill up its valence shell. So the first hydrogen atom is going to come over here, and so here we have the hydrogen atom, and hydrogen is very simple. It only has 1 proton, and so it also has only 1 electron, and so hydrogen is going to come over here, and it's going to share its 1 proton with the oxygen. So oxygen is a little bit closer to filling its valence shell, but it's not quite there, because right now it only has 7 electrons. 1, 2, 3, 4, 5, 6, 7. It still needs 1 more. So it's going to want to bond with another hydrogen atom. And so the other hydrogen atom is going to come over here, and here we have 1 proton, and we have the 1 electron. And now, if I look at each of these atoms individually, they're happy. My hydrogen atom over here has 2 electrons. This hydrogen atom over here has 2 electrons. Their valence shells are full. They're very happy. My oxygen atom also has a full valence shell, because now it has 1, 2, 3, 4, 5, 6, 7, 8 electrons in it. And so this molecule is a stable molecule. It's achieved a lower energy level than it could as separate atoms. So how does the polar part come into it? Well, what happens is the oxygen has an electronegativity of 3.5, right? We said that before. So oxygen was 3.5. Oxygen up here. And we said hydrogen had an electronegativity of 2.1. So that difference is great enough that what's going to happen is these electrons are going to spend more time around the oxygen than they are around the hydrogens. So if I look at the balance of positive and negative charges around the oxygen has 8 positive charges, but it actually has more negative charges when I count up all of the electrons, the valence electrons and those inner electrons. And so what happens is oxygen ends up having a slight negative charge around it because those electrons spend more time on this half of the molecule. When I go over to the hydrogen, because hydrogen has a much lower electronegativity, what's going to happen is these 2 electrons that it's sharing with oxygen are going to end up spending more time down there. And so this hydrogen is going to end up having a slight positive charge around it because it has a proton, but its 2 electrons are spending more time in a different neighborhood than they are in its neighborhood. And the same thing with this hydrogen atom over here. And so that's what creates the dipole within my molecule. If this is my water molecule, this is the hydrogen end that has a slight positive charge, and this is the oxygen end that's going to have a slight negative charge. And that is a polar molecule. So let's try another example of another polar molecule. Let's look at hydrogen bonding with chlorine. Okay. We have hydrogen and we have chlorine. So I'm going to look up on page 127 the electronegativity value for hydrogen, which is 2.1, and the electronegativity value for chlorine, which is 3.0. And I'm going to find the difference because I want to know what kind of bond this is going to form. So I always take my greater electronegativity value, I subtract the smaller value, and I end up with a difference of 0.9. So 0.9 is greater than 0.4, so we know it's not going to be covalent. It's too big of an electronegativity difference to be covalent, but it's less than 1.7, so it's not quite large enough to be ionic. And so what this is going to be, this is going to be a polar covalent bond. So covalent means that they're still going to share electrons, but polar means they're not going to share them equally. And so let's go ahead and draw our molecule. So we're going to start with the chlorine. And let's draw chlorine. Chlorine has 17 protons in it. Its atomic number is 17. And if I look at the atomic mass is 35, which means that it's going to have 18 neutrons in it. Oops, there we go. Okay. So 17 protons means it has 17 positive charges. I need to balance that with negative charges, so it's also going to have 17 electrons. So let's draw the electrons in their shell. So the first shell can only have 2 electrons. So we draw those 2. And then we have to start filling up the next shell. The next shell can have 8 electrons. So I have 2 in my first shell, 3, 4, 5, 6, 7, 8, 9, 10. I still need to add more electrons because I need to get all the way up to 17. So I have to add another shell. So 11, 12, 13, 14, 15, 16, 17. So here's my chlorine atom. It has 17 electrons. So 7 of those electrons are in the valence shell. So chlorine would be really, really happy if it could get 1 more electron in its valence shell. And so that's why the hydrogen comes along. So the hydrogen is going to come along over here. And remember, hydrogen only has 1 proton in its nucleus. It doesn't even have an electron. And what's going to happen is it's going to bond with the chlorine. The reason that the hydrogen wants to bond with the chlorine is because hydrogen wants to have two electrons in its valence shell, and it only starts with one. So hydrogen is going to offer to share its electron with the chlorine. Chlorine is going to offer to share one of its electrons with hydrogen. So hydrogen is happy. Hydrogen now has 2 electrons in its valence shell. Chlorine is also happy because chlorine now has 8 electrons in its valence shell. Because chlorine has a much higher electronegativity than the hydrogen, chlorine is going to end up hogging these electrons. It's going to be pulling those electrons towards itself. So these electrons are going to end up spending more time orbiting around the chlorine than they are around the hydrogen. And so what's going to happen is this part of the molecule is going to have a negative charge. And because the hydrogen doesn't have the electrons as often as the chlorine does, this part of the molecule is going to have a positive charge. So we have a dipole within this molecule. And the molecule is hydrogen chloride. And so if I draw the molecule, what I see is I see one region of the molecule that has a negative charge, one region that has a positive charge. That's a dipole. This is a polar molecule. So you would expect that hydrogen chloride is going to dissolve in water because it has positive and negative charges in it. And the water is also a polar molecule, and so the positive and negative charges in the water molecule are going to be able to pull apart the positive and negative charges of the hydrogen chloride. Okay, so hopefully that helps you understand polar covalent bonds. So remember, the covalent part means that the electrons are still shared between the atoms, but the polar part means that they're not shared equally. So one atom is going to hog the electrons, and it's going to have a slight negative charge around it, and the other atom is just going to have to not have those electrons quite as often, and so it's going to have a slight positive charge around it.